Excellent. So I'm guessing from the number of people in the room that people use Xarray and Dask a lot. And I guess we know this, that these two libraries pretty much underpin all of the analysis you do of model output in the climate world. And they're both an enigma. So you get introduced to these things and you get told, oh, this is the way to do it. Put this function on. And so we do what we've been told by mentor figures, and then it works. We don't really know why. And then we come back to it a little while later and it throws an error. And we've got no clue how to deal with that. So you go and find someone in the building who's the resident Xarray or Dask expert, and you get them to fix it, and they do some magic. And then you have functioning code again. You still don't actually know what it did. And so I can't tell you all of the fixes to every single error you're ever going to encounter, because these things have a magical ability to produce more errors than you should have thought was possible. But what I'm hoping is that I can give you the groundwork to explain what's going on in Xarray and Dask under the hood, such that you know where to start when you're looking at errors or when you're starting to write new code. So I guess the overall aim of this session is to be able to write faster and better code in Xarray. And so that's starting with why you want to do that, why it's worth the effort, and then what does it actually mean to be writing good code, to be writing fast code. And building on from that, thinking about what Xarray and Dask are. So what on earth is meant by lazy computing? Can I get a quick show of hands who's heard of the term and knows what it means? Cool, thanks. And then thinking about what's going on underneath and getting into that mindset of thinking, okay, I've written this function, what does it do? And then I'm going to talk about my 2 cents on chunking, which is kind of a black magical art that you think you know what you're doing and you try some stuff that it works and then it doesn't work later. And then at the end of all of this, once I've hopefully explained what Xarray is doing, I'd like to link that back to what you want to be doing in the first place. So almost all of my examples start out as averaging, where I'm just going to be talking through what averaging does, what the averaging is doing under the hood, and then how do we use chunking with averaging. But you probably want to be doing more interesting science than averaging. So at the end, I'm going to work through some increasingly complex examples of scientific analyses and how you can break that into the simple pieces that you need to be able to do it in Xarray. So I'm assuming that people come in with some Xarray Dask experience and some Python experience, but that doesn't mean I want you to sit there and every time I say something that doesn't make sense, you just ignore it. So if I say something that confuses you, or if you have a quick question, please ask it, please interrupt me and stop me, because I don't want to be jabbering off my own plane of existence while you're all sitting there confused together in the corner. And the other thing I'm going to start with, which is a little bit weird, is I'm going to introduce myself to the COSIMA community, which I don't think I've ever done in the COSIMA talk because I've met all of you at conferences, various bits and pieces. But I was actually a programmer long before I encountered climate science. So this is primary school Jemma. This is my first interaction with code. And we wrote a program called Cybersafe Server, which was classic 2000s, 2010s, the word cyber. The idea was if you want to play Minecraft without hackers, you should use your normal IP address, which changes every hour. And then we wrote a program that would Google your IP address and email that to your friends. Which the motivation was interesting, but we got this program working and we got a chance to present it at this big fair thing of other primary school students doing various bits and pieces on computers. So that's where I first met Python. And then another snapshot of my journey was I got really interested in informatics in high school. So this is writing programs to do things with data quickly. And I couldn't find any photos from this event, but I do seem to have kept every single program I wrote across the entirety of my last few years of high school and then during this summer school. So these are things like if you said something stupid at the party and you know a list of all the people who talk to each other, what are the chances that the person you meet now knows what you said last night? And so it's thinking about how do you turn that deluge of information into something useful. Now, obviously in the COSIMA community, everybody knows and nobody cares, but the point still stands. The last point on my journey here that I want to touch on is my first encounter with Xarray and Dask. So this was a project with Adele. Thanks for putting up with me. No worries. And that was just first encountering oceanographic stuff, trying to understand the Southern Ocean. Not only was just copying and pasting Adele's code and getting confused and getting slightly disgruntled about why some code was running really fast and then I hit load and then it crashed later. So all of the things that I'm talking about in this presentation, I've learned from you. This is from the community, from the bits and pieces that I've put together, from other people's questions that I've looked at, and then I've dug a bit deeper, and then I've learned something new that I didn't already know. So I've got community examples in here, and I've got, I think, a piece of code that I wrote for isotherms that's been copied off something Doogie wrote way back, tweaked a little bit. So thanks. And this is a great community. I'm so lucky to have been part of it. The last point that's not on this list that I might touch on is I've started poking around the Xarray and Dask code base in the last couple of years. It's surprisingly well commented, but it's also really weird that the stuff you have to do under the hood to say, yes, we're going to do this computation, but it's going to happen later. So I'm not going to go into that in great detail, but that's my justification for why I might know what I'm talking about with these things. Moving on to that, if I've said that I can tell you how to write faster or better code, why should we bother to do that? And I think that comes down to 3 reasons. The first one is that your time is valuable, and if you can write code that works faster, neater, first time, then that saves you going through and waiting for it or going through and debugging it. One of the things I was told at the informatics summer school I attended is that if you spend 5 minutes thinking about a problem, you'll generally save 20 minutes of writing code. So if you can think of a way to do the same thing neatly as opposed to the chaotic first hack you thought of, then it's probably going to be faster to write. So not only are you writing code that works faster as in it runs faster, but it saves you time writing it if you just think about it a bit first. Also, opening a Jupyter notebook and going Shift Enter 5 times and then waiting 5 minutes for it to run is the worst. I'm sure we've all done that you open up your cell and you run it and then there's not enough time to do anything else interesting, but you also have to wait for it to run. And so if you can tidy things up a little bit, so those first few cells take 20 seconds instead of 2 minutes, that makes life more pleasant. Obviously, if you're going to run something once and you could spend 30 seconds writing it a really hacky way, or you could spend 10 minutes writing it a beautiful, clean way, and then you run the code and it's done, and the faster one saved you 20 seconds, saved you 5 minutes. That's not a net sum. So I'm not saying that every single time you need to write the most efficient, the most beautiful, perfect code ever, but it's worth thinking about when do you want to write good code and when do you want to sink that upfront cost into writing something slightly tidier to make your life better later. The second point here is that if you can write code that runs faster, you can do more with it. So if you can write something that uses 10 times less compute power, then with that same SU budget, you can do 10 times more. If you can write something that works 100 times faster, you can do 100 times more. And if you can write something that uses 5 times less memory, and so now it finally fits onto the memory you can use on a single node, then that means that you can do analyses that weren't possible previously. And so writing nice code can enable new science as well. Any questions up until this point? Fast and good code. I've put together some examples with 2 libraries, which is NumPy and the Python timing library. And the first principle I'd like to start on here is that everything you ask a computer to do takes some finite amount of time. So here I'm asking the computer to print hi, and it's taken a very small amount of time. And I'm measuring this by saying T0 is some time at the start, and at the end I'm printing the current time minus T0. So this has taken a millisecond. If you say that x is 1 + 1, that takes some very small but finite amount of time. And if you do it more times, let's say we want to say x = 1 + 1 1,000 times, that's taken only 3 times longer because there's a lot of overhead with this printing stuff at the end, but it's taken a bit more time. We add another 0, takes longer. And so once you're doing something to every single grid cell for every single time period or other model analysis, then these really small function, like things you can do with code, can start to add up. And so I think it's useful to get in the mindset of, even if it takes an almost negligible amount of time, everything you want to do takes some compute time. So I shift to a slightly more complex analysis. Let's say I want to make 1,000 random numbers, and then I'm going to fill out an array of x values that is that number squared. We can run that. That's taken 2 milliseconds. Let's make it a bit faster. That's now taking 40 milliseconds, a 20th of a second. That's still small. There we go. Just under a second. So we've got some small compute here. And if you wanted to make this faster, the first thing you might try is looking at, okay, which bit is taking the time there? So I'm generating some random numbers and some empty zeros, and then I'm also calculating the difference. So now I'm going to print out the time after I've calculated those, like generated the random numbers, and the time after I've calculated x at the end of that. And if you print this, then the first bit is taking 0.1 seconds. The second bit's taking 0.4. So if you wanted to optimize this bit of code, you would say, this is the part that's taking longer, and that's the part that we need to care about. And as I'm sure you've all heard, for loops are much more expensive than NumPy code. This is mostly because Python is slow. Python code is slow, and there are other languages, I think Fortran or C, that are faster. And the NumPy library actually backends onto C. So when you do something in NumPy, you're giving NumPy instructions to go do something in C. And if you can hand it through together in like one big lump, then the Python bit of passing through that instruction is smaller compared to the doing the maths in the background. Whereas if you say, can you do this and this and this and do this in one again, then that Python time of passing through that instruction starts to take up longer. So we can replace this for loop with x is just y squared. And so that runs much faster. And now almost all of our time is being used generating the random numbers, and very little of it is being used calculating x. And so at this point, you wouldn't bother trying to speed this bit up. If you really wanted to get more efficient code here, you would look at what might be done in this section. And I'm just going to point out that even though vectorization is much faster, if we do the same thing again for 10 times as many numbers, then this second part, 0.3 seconds in there, it's now up to 0.4, which this is where that looked there. There's a little bit of stochasticity in there. The last one I ran was more obvious. I guess if I crank it up again by another factor of 10. So now we're getting 0.3 instead of 0.0 something or other. So vectorization sums still take time. They just take less time. And the last point I want to touch on when thinking about code running fast is I had something I needed to do for a whole bunch of months and a whole bunch of different ensemble members in a model. And in this for loop, I was doing something that takes a few seconds. So if you've got a few seconds of calculation in your for loop, there's not much point trying to take it out of the for loop and vectorize it because the overhead from running the for loop is smaller than the actual code you're running in the for loop. But in this analysis I was doing in here, it turns out that a lot of my time was loading data and less of my time was doing the sum. And I actually needed the same data for each month. So if you rearrange this and say, okay, I'm going to do my for loops in the other order, that means that I can load my data only once for each of these ensemble members and run the whole thing for all of the months at that point. And then that takes, maybe it still takes a few seconds, but it takes fewer than it did before. And so that's going to cut your time out of this loop some more. And with that, unless I have any questions on speed and NumPy, I'm going to move on to some Dask points. So we've got a few more libraries here. And the main thing I'd say that Xarray does is it gives us labels. That's why we use it. So if I load in some COSIMA data, I think this is one of the outputs from the 0.1 degree IAF run, and it should not be taking that long. Let's shut that kernel down, because it's now got several thousand random numbers that we generated earlier. So this is a sea surface temperature data set, and it's got dimensions with labels on them, and it's got some attributes attached to it. So instead of being a random bunch of numbers, it's a random bunch of numbers with labels. And that means that we can do things like take the average through time specifically, as opposed to remembering which dimension of the NumPy array is the time dimension. And so Xarray is a wrapper, a bunch of labels around a NumPy array or a Dask array. So if I generate some NumPy data here, let's say this is some seasonal cycle, the sine wave, we have a bunch of numbers, that's a NumPy array. And then I can turn that into an Xarray array by saying I have a data array, which is this NumPy array. It's got one dimension, that's time. It's got one coordinate, which is the numbers 1 through 12. So that's an Xarray array. Or alternately, I could take that, and I'm just going to break it into 3 pieces. And this is a Dask array with labels on the inside. So a Dask array, I think of it as a NumPy array waiting to happen. It's the numbers plus the things you might want to do to that in future, and it's got individual pieces. Now I'm just going to switch back to my slides there and talk about lazy computing, which is basically saying you're going to do something later. Instead of, like, if you're lazy cleaning your house, you'll do it later. If your computer is lazy computing, it says, yes, I know you want the average, but can we do it another time? So it keeps track of what it needs to do, and it doesn't actually calculate it until you go .load or .compute. And the other thing that Dask does is break things into smaller pieces, so different chunks. And the reason you do that is because sometimes you just can't fit everything into memory. So if I have these 9 numbers and I want to add them up, then you could add all of them up. But you could also break it into 3 pieces. And this is interestingly what you'd do anyway if you were given this list of numbers and told to add them up. I would kind of scribble down the sum of the first 3, sum of the second 3, sum of the last 3. And then you can get the same sum by then adding up the result of those smaller pieces. And in that, you haven't had to think about all of these numbers at once. You only have to think about the first 3, and then what's the sum of those, then add those up, add these up, and then add together at the end. So the default Xarray and Dask functions are ways of spreading out a computation you need to do into smaller pieces that you can then combine later. And this applies to a lot of simple functions. So if you want to find the maximum, you can also do the same thing where you just look at the maximum of each chunk, and then you find the maximum together at the end. Any questions so far? So when you have a whole bunch of these things, these individual bits and pieces to do the maths on, you usually use a Dask client to tell individual cores on your Guardi session or on your computer to go and do those. And the way you set that up, I would recommend just copying and pasting this code or whatever variant you have, which is just, I want to use a client from the Dask library. Threads per worker equals 1 just means don't try and have workers babysitting multiple threads, because stuff goes wrong sometimes and it's hard to predict and it doesn't seem to matter much normally. Memory limit equals 0 is please don't kill my session until I've actually completely run out of memory. Otherwise it tries to juggle individual cores that might be spending too much. And sometimes you just need one worker to go and do one really memory intensive task, and that's okay. Yep. Memory limit equals 0 is basically the Dask client is not responsible for my memory limit. Guardi can kill my. AMM is Active Memory Manager, which is some spin-off project that seems to help sometimes. It doesn't seem to hurt otherwise. So I usually leave that line in there. I think in some instances it can get you 20% memory savings, which can make the difference between your ARE session dying or staying up, but it's not that important. And then this last line is just to print it out. So now I have a Dask client, and I'm going to go over here and look at what that's doing. So I'm just typing in that dashboard link into this little red box over here. And then the ones I usually have up here are the progress bar and task stream. Worker memory can usually tell you if something's going to go wrong before it does. And the scheduler system, which is what's currently happening and what it's thinking about. And I might zoom out a little bit. Is that still legible, all of the text and code? No, you don't need to have included it in your ARE setup. The Active Memory Manager should just work once you've imported Dask distributed. Was the second half of that question important? Because I only got a preview. Yeah, so the question is like, what is the Active Memory Manager doing? I think what it does under the hood is just make sure that you don't have several workers all holding on to the same piece of information just in case they need it in future. And Dask is thinking about, okay, well, only this one needs to remember that information, the rest of you can forget it. So you have a little bit less redundant memory being used across different workers. So if we take that NumPy array wrapped in an Xarray data array from earlier, we could take an average through time there, or we could take the Dask array, which is the same one, but it's later. And if we say average through time, it's still going to give a Dask array. It says, okay, well, at the end of that, if I do that computation one day, baby, I will have 8 bytes in a single chunk. And it says that to get there is going to be 1 chunk in 3 graph layers. And if we look at what that 1 chunk in 3 graph layers means, it's going to spit out something like this. It says, okay, well, we're going to have all of these chunks. We're going to take the average of the chunk, and then it's going to combine them together at the end and take the average of all of those. So it's going to aggregate those numbers by taking an average, and that'll give the answer, which is pretty much what I explained earlier on the PowerPoint slide, that in order to do an average across lots of little pieces, you can average all of the pieces and then combine them at the end. This visualize function is kind of useful now to show what's going on. If you try and use it when you've got 200 chunks, what happens is it tries to draw this ginormous picture of what every single one of those little things is doing. It takes ages and it may not work. So I wouldn't really recommend. It's more useful often to look at this line. So 1 chunk in 3 graph layers is pretty small, should be fine. If you look at it and it says 400 chunks in 2000 graph layers, that's a solid chance that your code is going to hang for a while and then possibly not work. And it's useful to think about where those might be coming from and if you can speed that up or make fewer chunks or fewer graph layers. So that might be if you can afford to load something earlier because it will fit into memory, that'll stop your Dask graph getting too big. Or if you can use select early on and shrink stuff down to be smaller, then it'll try and do less maths on the whole thing. Other tricks along those lines can make bits small. It's roughly equivalent to steps. So this is 3 layers, even though it's 2 steps. I don't know exactly how it translates. So then we can take that Dask average and we can put dot load. So that means, no, actually now we're doing the computation. And so then you can see this happening over on your Dask cluster. That it had to think for a little bit while it worked out which of the cores were going to do what maths. Then it's done 4 very, very tiny maths things and then merged them at the end. Now, obviously, if you have 12 numbers, it's faster to just do them all at once. It's not worth the extra time working out who's going to do which bit piece. But I wanted to show that as an example. So let's use something slightly bigger. So this is a bunch of data I also pulled from ACCESS. That's a question. While that's loading, I have a question in the chat for what's the difference between compute and .load. Load returns the value and saves it in the same thing. Compute only does one of those. Can I remember which? I think it only returns it. So if you use compute and you forget to put something or other equals, then the original thing stays unloaded. And if you meant to load it and keep it saved in the data like variable, and then you forgot to do that and you wasted 3 minutes waiting for it to load, it's really annoying. So I always use .load because it saves it as well as returning it, but I can see that there might be instances otherwise. Persist theoretically shoves things onto individual cores. I haven't personally gotten it to work well. Sorry, I'm just reading the question in the chat. A Dask cluster can be spun up outside ARE. If you're using a notebook elsewhere, you'd use the same lines. If you're using a Python script, you do something along the lines of and then put all of the rest of your code in here.
Yes.
A tutorial. If you want to use Dask outside of a notebook, go find that. So now I have some ACCESS-OM2 data. It's 81 gigabytes. It's in little chunks. So the overall data array is 30 times 75 depth, 2,700 in the Y dimension and 3,600 in the X dimension. And that's broken into chunks of size 1 in time, 19 in depth, 135 in latitude, 180 in longitude. So those are relatively small pieces, which might be an issue, and I'll show why in a couple of minutes. And that's not me deciding how to chunk that. That was previously how the data has been chunked on disk and it's reading in automatically. I'll show how to choose your chunks in just 2 seconds. Yes, there are absolutely optimal chunk sizes, but it depends on what you're doing. The rule of thumb I've heard is somewhere between 100 megabytes and a gigabyte. The rule of thumb I use is the thing that stops the scheduler hanging for ages and actually runs, but doesn't use so much memory that it crashes. And that seems to vary a lot based on what problem you're encountering. So we're going to take a subset of that runs without crashing, slice it, and take the average, and then that's still a lazy computation. That at the end, we're going to be left with 46 kilobytes of data, and we're left with 2 chunks. That's 120 chunks in 26 graph layers, which is probably still fine. I'm using a slightly different way of timing here because it's faster. If you want to do like faster to type, if you want to use just time one line, you can put %sign time at the start of your line and it'll tell you how long that takes. So in this instance, I'm taking my temperature, I'm selecting surface ocean and a chunk of latitude, taking the average in longitude, and then hitting load. And so that CPU scheduler is going to spike for a moment as it works out what to put where, and then drop back down again. So often if something's hanging for ages, the CPU will spike right up and stay at 100% for ages. And that tells you that your Dask graph is probably too big, your chunks are probably too small because it's spending too long thinking about where to put all of those pieces. Looking at this running, it's taken 15 seconds. So again, and then you can see that it's got some labels down here, and things that are taking up lots of space up here are the mean of the chunk and then pulling things together at the end. Ignore that chat question, it looks like a generic set of replies. If we zoom in on this, I do that. No, sorry. If I wave my cursor over here, you can see that a lot of these things are taking about 23 milliseconds, 10 milliseconds. So that means that all of the individual pieces are running really quickly. And a good rule of thumb is the overhead to put all of these pieces on individual workers is going to be a couple of milliseconds. So we've got a non-negligible overhead for just allotting out all of these individual tasks. And so I think most people would be aware that the way to fix this is to make those chunks bigger. But the thing that seems to have almost no documentation on that is that this is the wrong way to do it. So the logical step would be like, okay, take my data, chunk it to a normal chunk size. So we'll say that I want to have my latitude chunks all in one go because I know that I'm averaging across latitudes. So we may as well use all of the latitude. And then we can do individual pieces at different longitudes. So I just said that backwards, didn't I? Yeah, cool. Okay. Sorry about that. So you could chunk XT ocean to be all one piece. -1 is no chunks, just all of it's one go. And then do the same selection, the same average. And now we've got even more bits and pieces here. And so what it's doing is it's loading the thing in with the wrong chunks and then trying to re-chunk it and then doing the maths. And that actually takes, is it very slightly longer? Very slightly longer. It's not helping us at all because we have all of the overhead to re-chunk. So if you want to do something from data on disk, you need to tell it what chunks to use when you load it. And there is a keyword for this going into intake as well, but I haven't used it recently, so I didn't want to give you false information there. So loading the same data, but I'm specifying my chunks. I want time in blocks of 12, say yearly, and I want my ocean in one piece in longitude. If we load that, then we now have data, and you can see from the picture that it's now got really long chunks in XT ocean, and you can see from the description here as well that the chunk is now 3600 in XT ocean. Parallel equals true means when you're opening this, can you spread it across all the different workers? It probably doesn't matter much in this instance, but I've found circumstances where it makes things much faster. So then we can do that same sum. And because we've got much bigger pieces, you can see that all of these individual tasks are taking half a second instead of 20 milliseconds. And that means that overall the whole thing's running in 6 seconds, whereas before we were running in 14 seconds. So making your sum into big enough pieces can help you speed things up overall. And that, I'm not sure I can be bothered running this line, but you can then take the average of the whole thing instead of sub-selecting a particular latitude band, and that does still run. Whereas when I was messing around with the other one, I had to choose a smaller latitude band. Otherwise, it would try to do everything in little tiny pieces, And it just sat there scheduling for 5 minutes, 10 minutes until I gave up. So that's another example of when you can make something possible that wasn't possible previously. And the last example I'm going to throw here is just the really extreme other end. If I say I want no chunks, which isn't quite going to work because it'll max out at the size of the files and it'll still load each file into chunks. Then we can load that, loads pretty quickly. But because I'm only selecting the top layer of the ocean depth, but I've chunked all of the ocean depth into one piece, it's going to hang for ages because every single one of those sums, like averages in longitude, it's grabbing all of the ocean depth, loading it in, and then just doing the top bit. Will, yes. Put the chunks in the chunks argument.
Okay.
Pre-process is also a good way of making things chill out by the time you actually try to do analysis later. So if your pre-process is just select the first one, then it'll do that as a separate step, and it's a way of separating out so the Dask doesn't get too confused with all the different things it needs to do. This is still having a think here. So because I've broken this piece into too many big pieces, then trying to do that same calculation, even though it's only 10 individual jobs or individual tasks, it's not getting to that point. And you can look down in this bottom left-hand corner that this worker is now up to, I think, holding on to 7 gigabytes, and now it's died because it's no longer here. We're down to 3, and then we've started a new one underneath. So if your chunk sizes are too big, each worker tries to hold too much memory, and it's going to take too long to do anything or possibly crash. Might stop that as opposed to leaving it doing terrible things. Let's switch back here. Any further questions on that notebook before I go on? This is an example of where it could be useful to think about the underlying code. So this was a bug that Hannah identified. Bug is a questionable interpretation, that if you try and find standard deviation of salinity, there are some instances in which you can get NaN values or really noisy output. And when I suggested what might be going on here, a lot of people interpreted that as the Xarray code is wrong, which is not, I think, quite right. So in order to explain what's going on here, I just want to look at how we calculate variance. And if you look at, like, normally how we think about that, the way it's taught in maths is that you calculate the sum of the difference from the mean squared and then divide that by the number of things. And because difference of squares applies to brackets, you can actually break this into two sums, where it's the sum of all the bits and pieces minus the sum of the mean. And that's mathematically equivalent. And this is often how it's implemented computationally, because in this way, you only have to open each chunk once. So you open it, you calculate the sum, you calculate the sum of the mean. And then when you get to the end, you can combine all of those sums together and do your final division. And so if you do it this way, and then this sum of the mean is really, really big, and the sum of the values is really, really big, and the difference is small, then you can accidentally end up with that last decimal place in the computation being dropped off the end. So if this is 200,000, this is 200,000, and the number you're looking for is like 0.3, then there might not be enough decimal points for the code to hold on to it. And so this is a reasonable interpretation of how to calculate variance up until you hit enormous numbers, so salinity being 34 or 1,000 in the deep ocean where the variance is tiny. And that's an instance where just knowing a little bit about what's going on underneath the hood can make it easier to explain what's going on at this very surface level. Is that a question? Save numbers, you save them as like a 32-bit float or a 64-bit float, right? So that means there's 64 bits of information. And that means that there's a certain number of decimal places, and then you can't save any more decimal places. So if you're calculating the sum of some numbers squared, and then you have lots of numbers squared, then you end up with a really big number. And this one here is also a really big number. And the difference between those is a really small number. It might not actually be there in the decimal places. It might have dropped off the bottom. Make sense? Chunking. I don't think there's a nice way to summarize this easily. These are probably the things that I would consider most important in my experience, is when you choose chunks, take a look at what is already on file, so what it loads from a single file automatically, and try and have a number, like an even multiple or an integer multiple of those chunks, so that there's no extra effort into massaging the gaps. You want to use slightly more that's on often you need to use slightly bigger chunks than what's on file, but you want to be still trying to fit into how it was originally saved. As I touched on, if you try and rechunk after you've opened a data set, that can cause overhead. So you want to chunk either as you open the file, specify the chunks keyword, or in some instances, if you have a small data set that you need to do something big computation to, you might want to load the data set and then chunk it. And that is also fast enough to be useful. But in between these, if you open a file and then try and rechunk it, is unlikely to help. All of these are guidelines. It's useful to check what actually works for your particular analysis and your particular data set. So I would always start by opening this very small subset of the file and checking what you want to do and seeing how that looks on the task stream if you've got big chunks, like taking a normal amount of time to compute, or lots of little tiny slivers. And so always look at that. And if you just have those task stream and the progress bar on the side of your screen, then you can get a feel for what's normal computation. And if something looks funny, then you can start to dig into, okay, that might be a problem. How do I think about what's going on here? What might I need to change? If you want your kernel not to crash, and you want to load a data set, then a very good rule of thumb is whatever data set, so it's an 80 gigabyte data set and you want to load the whole thing into memory, it's probably going to take 160 gigabytes of memory. That's a really ambiguously worded point, I'm sorry, because if you have things in Dask chunks that are being done individually, then that won't use all of your memory. It'll do all the bits one by one and then combine them, and you won't hit too much memory at that point. Sometimes it's really hard for me to say when this is the case. It's going to take too long for the scheduler to give individual bits and pieces, or too long to combine, and it's not helpful. And it's worth just remembering that's a possibility. If something's taking long and you can't work out why, try doing the same thing without Dask and seeing if it fixes it. And on that same point, sometimes it uses your time better and the Dask scheduler is not helping, and you just put something in a for loop, do it once. So make this calculation, save the output, and then you have the output that you can do your further analysis on later. And that shouldn't be the case, but sometimes it is faster just to do it that way. Any further questions about Dask and Xarray working? Sorry, Adele. So do I have any advice about choosing ARE session size and number of workers? Experiment is probably my only advice. See how long it takes on different things. Once you have something working on a small session and it looks like your chunks are reasonable, they're taking a reasonable amount of time, it'll probably scale up to a larger ARE session and take you less time overall. But you want to check that because it might not work. Can the Dask cluster be spun up similarly outside? I got that one, right? Are there any questions in the chat that I've missed? Because I can't scroll through the chat. Are you sure it's file writing to disk, not the fact that it needs to load before it writes to disk? Because in my experience, every time someone comes to me and says this is taking ages to write to disk, what they mean is this is taking ages to load, the whole thing was lazy. And then when you try and write to disk, it goes, oh, I have to calculate this now. And then it's calculating it, and the writing it out at the very end is not the problem, it's the calculating.